I am delighted to bring Dr. Bill Brown's wind tunnel to the Institution of Civil Engineers as part of our broader engagement around the Infrastructure Learning Hub. This fabulous exhibit is a live exhibit. It works, and it was built by Bill and his team to solve a problem he had over 50 years ago. He wanted to design the most innovative bridge deck in the world ever. He did, and that bridge deck is now used across all suspension bridges, fundamentally, that are built today. I am delighted to have this fantastic piece of equipment and some people who worked with Bill, and you'll hear from them later, Stafford and Harvey, and they will show you how this works. And they'll also explain the story as to why Bill wanted to build this. This wasn't about an engineering masterclass. This was about pragmatic solutions to an engineering problem of the day. And the lessons learnt yesterday are being applied today.
Well, I first met Bill Brown when I joined the company in 1961. Bill then was a senior engineer. I was a lowly graduate who knew very little. Haven't changed much actually. But Bill was this chap, brilliant fellow, very advanced, always looking for something new. He had a wide range of interests. I remember him always dashing off to Formula One races in Zandvoort and all sorts of places. And his interest in aeroplanes and fast cars and old cars. He had a wide range of interests. His knowledge of engineering was unsurpassed. You knew him a bit later, didn't you?
Yes, I mean, I think this is where his basic interest in aerodynamics came forward, and that wasn't just bridge decks, it was cars, it was aeroplanes. He was always looking at configurations, and he was always looking at design form, always looking for a better solution, a more efficient solution. He had this restless mind, and even when you thought you got the answer, he was always wanting to try different things. And sometimes a lot of it was blind alleys, but very occasionally you had this wonderful moment when you had this breakthrough, and you actually made he improved the present design by an enormous amount. I met Bill in 71 when I joined the company. I didn't work with him there particularly. He was away working on the Bosphorus bridges, but I rejoined with him and worked with him on a one-on-one basis in 1989, 1990, when he'd formed his own company, Brown Beach. So in fact, I had a very close relationship with him for about 10 years, where we worked on diverse bridges, particularly suspension bridges, and it was wonderful to work with him and follow his design mentality in finding the basic solution, which was the Messina Bridge, basically a solution for the Messina Bridge, which was a bridge which has everything. It was not only was it a clear span of 3 kilometres, it was over a very deep channel, it was in an earthquake zone, very high wind velocity. I mean, for a bridge engineer, that was probably the ultimate goal to solve. And I think this is what he did, working with the Italian engineers. He headed up the designs to come up with an aerodynamically stable deck. For a bridge of that length, aerodynamics actually governed the design. The statics are something which can be overcome in a more conventional manner, and it was Bill who found the solution with the help of the wind tunnel which we had in our office here.
It was the only way of dealing with that before the wind tunnel was to use the one wind tunnel at the National Physical Laboratory. You had to book a time there and you got a time span, and that's what you had. And in fact, that was one reason why the Severn Bridge section came into being. The Severn Bridge was going to be a lattice-type girder, like the Forth Bridge, made of grillage, quite a heavy, cumbersome thing. And Bill was thinking about an aerodynamic sort of airfoil deck. And they went, he and Sir Gilbert Roberts, who was the leader of that part of the company at that time, went to test this, the original section for the Severn Bridge at the physical laboratory. only to be told that someone had dropped the model. And as you can see, the models we're using are quite flimsy, made of balsa wood. And that was it, and their slot was lost. And Bill said, well, I've got this new idea about the aerofoil deck in the back of the car. Let's use the time. So we went out and got the car and used their half hour or whatever it was and tested the Severn Bridge section. And it worked beautifully, up to 125 miles an hour. And from that time on, the design was changed to the aerofoil deck, which, as you said earlier, was the first aerofoil deck ever used. And every suspension bridge after that carried on in the same mode.
Certainly in developing the Severn streamlined box section, which had a lot of advantages over what was now before was considered to be the solution, which was a truss. Bill realised when he was doing this that the one problem he had is being able to design these decks aerodynamically. And how could you actually do that if you were just at a desk, or even to try and calculate aerodynamics and the effects of aerodynamics in those days was not possible. And so this led to his idea, or his solution was to build his own little wind tunnel and keep that in the office. And his particular thought there was to just use it so that he could do comparative analysis of different shapes. So in other words, we could put one shape in and then measure a wind speed, put another shape in, measure another wind speed, see how much it moved. But the more we got used to this, the more we started developing wind tunnels. In fact, this is the third one that Bill and I actually built. We suddenly realised that we were getting better and better, more accurate solutions. And then we started modelling the mass, modelling the frequencies, and so we were getting a pretty good idea along the same lines as that industrial wind tunnels were getting. And so we could do fast comparisons of new ideas. When Bill came up with a new idea, I could put it in the wind tunnel, and we could have it tested, but also we could keep tabs on how well it was doing from a full-scale point of view. So this is the tunnel that Bill finally came up with. In fact, it was the third tunnel we'd actually built in High Street, Kensington, in our offices. But by this time, we were getting confident in the results of the previous tunnels. We basically bought two variable high-speed fans, variable speed high-speed fans, to suck the air through the tunnel. The idea is to try and get the airflow as smooth as possible over the model. The models themselves were obviously much smaller than an industrial model, so we had to try and get as uniform an airflow as possible, and also measure the airflow accurately. We had various embellishments where we had a smoke-making machine, and we could blow smoke over the models just to see where the streamlines went over the various boxes. This did cause various problems in High Street, Ken, when we opened the windows, but generally speaking, it pretty well worked. And we were able to quickly build a model, build an alteration, put it in the tunnel, and we very soon see whether it looked as if it was an improvement or not to what we had before.
As Stafford just said, we can design bridges using calculations, stresses and strains, and so on. And wind speeds, the wind force on a bridge is significant. And I can use the Tacoma Bridge in America, which was built in 1940. That moved from the old lattice girder, trying to make the decks lighter. The main object of these bridge advancements is to make the span bigger, and that means making the deck lighter, the roadway lighter. And he went into a system which had, instead of a lattice girder, two large I-beams at each side. I think you could see that from here. One I-beam on each side with the cross girder. Much, much lighter. And this was designed, and it took all of the traffic loading, its self-weight, wind loading up to 125 miles an hour. Absolutely perfect. Calculations were wonderful. It would work. But I think about 3 months after it was open to traffic, in winds of 42 miles an hour, it blew itself to pieces.
The Tacoma Bridge, just to embellish it a bit, was designed by a brilliant engineer called Moissieff, who was in fact a very good mathematician. What he designed was the perfect static solution, as Harvey said. But in doing that, the static solution was basically 2 girders with cross beams, no torsional stiffness, and bluff sides. And it was the bluff sides which caused the eddy shedding and caused the instability of the deck at a very early wind speed.
And that was the first time, that was 1940, the first time we all got an understanding that there was a problem with aerodynamics. And from that point, bridge decks got big and heavy and lattice girder again, until the 60s, when Bill Brown came up with this aerofoil deck, which is now the future of bridge decks.
So this was the accepted solution following Tacoma, which is a classic truss. This model actually is work that we did on the Tagus Bridge, which was built in the 60s, and we basically had to strengthen it and in order to take a train to go through the middle of the truss. That's by the way. But that was the conventional solution. Now, it is actually in a very poor state of affairs because it's been used a lot. Now, if we compare that with the box solution, which was Bill's innovation for the Severn Bridge, you can see how clean the lines are, how much easier it was to fabricate and also to construct and install. Also, it was a lot shallower, so the deck was shallower and attracted a lot less stress, and easier for maintenance. It had a lot of advantages. This was the Severn Bridge, and if you look at the previous bridge to that, was the Forth Bridge. The Forth was a truss solution that followed conventional lines. The Severn Bridge was going to be a truss until the accident in the wind tunnel, and so you can quite easily compare the 2 bridge decks to see the difference. When Bill was asked to look into the Messina Straits Bridge, it was 3 times longer than any conventional bridge. And whereas this deck had been used for longer bridges like the Humber Bridge and the Bosphorus bridges, this could be done by deepening the deck to make it more torsionally stable and widening it. But when it came to Messina, it was quite evident to Bill that this solution would no longer be efficient. It was meeting force with force, which was never his idea of an engineering solution. He had to find some way of overcoming these very strong aerodynamic forces which were needed when designing something like Messina. He looked at various things, and I remember in 1971 he was looking at various hangar configurations, various cable configurations to try and improve things. But it was back then that he'd realised that the vented deck was the solution. In other words, a deck which wasn't solid like this, but could let the air pass through it to reduce the aerodynamic forces. And this is when I came to him. This was in 1989. He'd just been asked to start looking at the new forms of Messina deck, and this is when we realised that the best way of doing that would be with our own little tunnel, rather than trying to wait and rely on the more industrial-sized wind tunnels.
Well, I think that's probably enough talk, and we'll now have a demonstration of the wind tunnel in action. We've decided to show, first of all, the Tacoma Bridge, which is the Tacoma Narrows Bridge, which blew itself to pieces at wind speeds of about 42 miles an hour. We'll then follow that directly with the Severn Bridge deck, which you'll see is absolutely rock solid at 125 miles an hour and more. And then we'll follow up with the Messina model, which needed a gap down the centre between the 2 parts of the bridge. And that will show how it works without the gap and how it works with the gap. This is just general improvements, as staff had said, as time went on in looking at the design and being able to just do that, take the gap away and have a look at it in the wind tunnel.
Okay, so here we have a model of the Tacoma deck. And as we said, the Tacoma deck was basically two bluff plate girders and with a cross beams and a deck between. So we'll just turn the speed on very low. And the problem with this shape is because it's not aerodynamic, it immediately has vortex shedding off the edges of the girders. Now when this eddy shedding coincides with the frequency of the deck, it begins to twist. The deck has very little torsional stiffness, and so immediately you see, even at a low wind speed, the deck is starting to move. If we now increase the wind speed, this fortifies the eddy shedding, and the deck movements amplify, and eventually the movements become divergent, which is a form of flutter. In fact, if you look at the Tacoma Narrows on the film, you'll notice that the center line of the deck doesn't move in real life, which is the same as what's happening here. As you can see again, the amplifications are getting stronger and stronger without me having to increase the wind speed. And that is a result of a deck which has got no aerodynamic shape to it. And it was at this point that the industry realized the importance of aerodynamics on the design of suspension bridge decks, or any flexible sort of deck. So now we have a model of the Severn deck, and this, as we said, is the first plated structure, which is a torsionally strong box, but a very shallow box, and we can now compare it with the behaviour of the Tacoma Narrows type of section. I'll just put it on at the same wind speed. As you can see, it's now going into flutter, but at a wind speed over twice the previous one. So that shows you a very simple comparison. I mean, to do a real comparison, you'd have to model the vertical torsional frequencies and the mass models. But in fact, if anything, this is a conservative comparison between the Tacoma Narrows deck and the Severn deck. So this is the final configuration of the Messina Straits Bridge deck. So there's three solid decks, two carriageways and a central box for the train. But the secret here is the two vents. In other words, the separation of these decks, which gives it the added stability. And the size and the position of these vents was determined by numerous tests in this wind tunnel. So this test will demonstrate how a vent is effective and how it works. We have two boxes here, and for the first experiment, we've closed the vent off. So in other words, it's a solid deck, and then we'll see where this flutters. We'll then take off the covering of the vent and be able to have a direct comparison with the aerodynamic performance with and without the separation. So I'll just start the fans. These are the pitot tubes, which are the results of the pressures from the pitot tubes, which basically translate into wind speeds. Okay, now the wind speed is increasing. The deck is still reasonably stable, but you can see that it's beginning to have some excitation with the wind. And this movement is classic flutter. It's up and down and twisting at the same time. Okay, I'm now going to increase it. You see the amplitudes increase, the flutter builds up, and now it becomes divergent, and the deck would destroy itself if we didn't stop it. So now we've removed the covering from the vent, which is now active, and we have two boxes separated with an air gap. I've left the controls at exactly the same wind speed where the previous model fluttered. So when we turn on, we can see whether this will flutter at the same time. So now we've removed the covering of the vent, and so we have two discrete boxes with an air gap in between. I've put on exactly the same wind speed at which the previous model fluttered. And as you can see, with the vent active, the model is now stable. I'll now turn the wind speed up again to see if we can get this one to flutter. The wind speed, this indicates the wind speeds. It is now well past the model of the previous flutter speed of the previous model, and we still have an aerodynamically stable model. In fact, we're now at a maximum wind speed, and we still don't have flutter. It will flutter eventually. It's just off the scale of our particular test. There, you can see it's not far off flutter if I just move it, but it's still not. You're not getting divergent amplification. So that demonstrates how effective an air gap is, and this is the solution that Bill came up to for very long span bridges, where basically the resonant frequencies are so low in a long span bridge, the aerodynamics become the overriding factor which govern any design. Okay, so there you have it. We've shown you the aerodynamic characteristics of three different deck designs. We've described the structural behavior of these different decks, and so you can see the progression of how the design has evolved, and also the innovative features introduced by Bill to overcome the challenges of long span bridges. In other words, looking for new solutions and not just extrapolating old ones in an inefficient manner.
Okay, we're both delighted to see this wind tunnel here in the institution building, where it's on show to many budding engineers. We're extremely pleased also to learn that it's going to a school of engineering in the East End of London, where it will influence, we hope, many young engineers to attract them into bridge design and engineering design anyway. And hopefully one of those in the future will use this machine to perhaps design an even better structure than we have today. We think this is a great asset for young engineers in the future.